All right, let's talk about a technology that could totally reshape our world: quantum computing. But here's the thing: to really get it, you kind of have to forget everything you think a computer is. This isn't just about making things faster, it's a completely different way of processing information itself.
So let's just jump right in with one central kind of mind-bending question. What if a computer wasn't stuck with a simple on or off? What if it could be both at the exact same time? That single idea, right there, is the key that unlocks the entire strange and powerful world of quantum computing.
To even begin to answer that, we've got to get one thing straight. We are not just talking about a faster machine here. This is an entirely new kind of computer. Look, I really want to hammer this point home. This is not an incremental upgrade, like going from your laptop to some giant supercomputer. No, this is more like jumping from an abacus straight to a smartphone. It runs on totally different rules of physics. Okay, so here's the absolute core difference, and we can boil it down with a simple analogy. Your phone, your laptop, all that stuff, it all runs on bits. And a bit is just like a light switch. It's either on or it's off, a 1 or a 0. Simple. But a quantum computer uses something called a qubit. And a qubit is way more like a dimmer switch. It's not just on or off, it can be on, off, and every shade in between all at once. This ability to hold multiple values simultaneously is where all its incredible power comes from. So how in the world does that dimmer switch actually work? Well, it's powered by two of the absolute strangest and, honestly, most fascinating phenomena in all of physics. First up is superposition. Now, this is just the fancy official name for what we were just talking about: a qubit existing as both a 0 and a 1 at the same time. By putting a bunch of qubits into superposition, a quantum computer can basically check out a huge number of possibilities all at once. It's a kind of parallelism that's so massive, I mean, truly massive, that classical computers can't even come close. And then you have entanglement. This is the one that Einstein himself called spooky action at a distance. It's wild. When you entangle two qubits, they become fundamentally linked. Whatever happens to one of them instantly, and I mean instantly, affects the other one, even if they're on opposite sides of the universe. It's this bizarre, spooky connection that lets them perform these incredibly complex, coordinated calculations that would otherwise be impossible. And this quote from the physicist Charlie Bennett is just a brilliant way to flip the whole thing on its head. He says, instead of asking why quantum computers are so fast, maybe we should be asking why our normal computers are so slow. I mean, the universe operates on quantum rules, right? So maybe our classical machines are just a really limited, simplified version of what nature can actually do. Okay, so we've got these weird, spookily connected qubits. Super cool. But so what? What can we actually do with them? What kinds of massive problems can this new power actually unlock? Well, the theory behind all this isn't exactly new. People were laying the groundwork for these quantum algorithms decades ago. But then, in 1994, a physicist named Peter Shor came up with an algorithm that made everyone sit up and pay attention. Big time. Because it was aimed squarely at the foundation of our modern internet security. So here's the crucial thing about Shor's algorithm. It's designed to factor huge numbers way, way faster than any normal computer ever could. And why does that matter? Well, because the encryption protecting your bank account, your emails, your entire digital life, it all relies on one simple fact. It's incredibly difficult for normal computers to factor those huge numbers. A big enough quantum computer running Shor's algorithm could, in theory, just shatter that security. But it's not all about breaking codes. The real promise, the truly exciting part, is about solving problems that are currently impossible for us. I mean, think about discovering new drugs. We could simulate molecules perfectly to invent new medicines, maybe even cure diseases that have stumped us for decades. Or in material science, we could design brand new materials from the atoms up. Think self-repairing metals or hyper-efficient solar panels. For logistics, we could solve these insanely complex routing problems for shipping, making everything faster and dramatically cutting our carbon footprint. And in finance, we could build models to predict markets with an accuracy that seems like pure science fiction today. Now, with that kind of potential on the table, you can bet it's kicked off an incredibly intense global race. And it's not just between countries, but between all the tech giants to be the first to build a truly working quantum computer.
A huge moment in this race came back in 2019. A team from Google and NASA made a massive announcement. They claimed they had achieved quantum supremacy. Their processor, named Sycamore, did a very specific calculation in just a few minutes. That same calculation, they said, would take the world's most powerful supercomputer about 10,000 years to finish. But the story wasn't quite that simple. IBM, Google's biggest competitor in this space, fired back almost immediately. They basically said, whoa, not so fast. They argued that if you optimize that classical supercomputer for this specific task, you could get it done in just 2.5 days, a whole lot faster than 10,000 years. This kicked off a massive debate and really just shows how complicated and competitive this whole field is.
So why is all this so ridiculously hard? Why is there even a debate? Well, it all comes down to one major villain in the story, something called quantum decoherence. See, the very things that make qubits so powerful, their superposition, their entanglement, also make them unbelievably fragile. The tiniest interaction with the outside world, like a little bit of heat or a stray vibration, can make a qubit decohere and lose all its quantum information. That creates errors, and it is the single biggest challenge that engineers are trying to solve.
So, where does that leave us? Well, we're basically standing on the edge of a new era, facing both this incredible promise and some pretty significant peril. To build a quantum computer that's actually useful, researchers have to conquer three monumental challenges. First, they have to beat decoherence by perfectly shielding the qubits from all that outside noise. Second, they have to figure out how to scale up, to go from the hundreds of qubits we have today to millions of them, all working together. And finally, they have to invent really clever error correction systems to constantly fix the mistakes that noise is always going to cause. When you boil it all down, quantum computing really is a double-edged sword. On one side, you have the promise, this incredible power to solve some of humanity's biggest problems in medicine, energy, you name it. But on the other side, you've got the peril, a tool that could potentially break the encryption that protects our data, our money, and our national security, all in an instant. And this brings us to the final, crucial question we have to ask ourselves as this technology starts to become real. It's a race between creation and destruction, a journey that really forces us to wonder, will quantum computers build our future, or will they break our present?